Hey guys, welcome to Unit 4, Section 3. We are going to be proving quadrilaterals are a parallelogram in this one. So if a quadrilateral has any of the following six, then we can conclude that it is a parallelogram. A lot of these are just the properties that we've already talked about. There is going to be one idea though that is enough to prove, and it's a combination of two properties. So number one, opposite sides parallel. That's the definition. That's where it gets its name, parallelogram. So if we can prove that both sets of opposite sides are parallel, we know it has to be a parallelogram. The next option is opposite sides are congruent. Both pairs of opposite sides, not just one pair. Number three is opposite angles are congruent. So with opposite angles being congruent, we know that has to be true for both sets. Again, another thing that we've talked about, that's a property. Number four is the weird one, so I'm just going to circle that one and star it. It's one pair of opposite sides parallel and congruent. So you can pick a pair of opposite sides that you know you can prove are parallel and congruent at the same time. Then you don't even have to worry about the other set. Number five is consecutive angles supplementary, so those side-by-side angle kind of things. Those at a 180, that one's harder to prove. We don't usually use that. And then diagonals that bisect each other. We will use that one as well. But any of those six combinations will prove that a quadrilateral has to be a parallelogram. So here's some examples with this. Sorry about that. If it lets me zoom in. Is the quadrilateral a parallelogram? Yes or no, and how can you be sure? With the first one, we notice right away that we have angles that are side by side. They're not the same, but we do see that opposite angles are congruent, and that's actually enough to justify, what am I doing? Those aren't congruent with each other. We just need one. So 65 and 65 are congruent, 115 and 115 are congruent. Therefore, we can say opposite, and well, we would say yes, because opposite angles are, and we can just put the symbol, congruent. For the second one, we know that those two sides are congruent, and those two sides are congruent. Therefore, by opposite sides being congruent, we know it has to be a parallelogram. Yes, opposite sides are congruent. Let's go ahead and do the next one. Is this is the quadrilateral a parallelogram? Yes or no, and how can you be sure? The first example, we notice right away we have one pair of parallel sides and one pair of congruent sides. But since they aren't the same set, we can't actually conclude. So this one is no. And if it's a no, I mean, it's just because there's not enough information or we don't have one of the six. So we don't really need to explain that part. This one, however, the second one, we know that they're both 30, so they're both congruent and they're parallel. Since it's the same set that is parallel and congruent, this is enough to prove that triangles are congruent. So this is yes, one pair of opposite sides is parallel and congruent. And then the last one here, we notice that the diagonals are crossing each other. Looks to be that this segment is congruent with this segment, and this segment is congruent with this segment. Therefore, the diagonals actually bisect each other, which is one of our properties. So this is yes, diagonals bisect each other. Again, we are just looking for one of these 6 to justify that it's a parallelogram. Now, those were pretty simple examples where we only had to do one step or change one little thing. Now we're actually going to do some proofs with these. So the first proof, it tells us that ABCD is a parallelogram. We want to prove that 2 triangles are congruent, knowing the fact that the whole thing is a parallelogram. So just like usual, we are going to do our given, which in this case is ABCD is a parallelogram. The reason is because it was given to us. Now, for the next lines here, we can say that since we know ABCD is a parallelogram, we know any of the 5 that we talked about up here, or any of the 6, excuse me. So we can use all of those because those are all the definition of a parallelogram. It's not letting me move it very well. Sorry about that. Okay, so now that we know that it's parallelogram, let's use that definition to help us. The easiest way that I would approach this is knowing that opposite sides are congruent. So DC has to be congruent with AB. Let's say DC is congruent with AB. And that's because it's the definition. You can abbreviate if you want, definition of parallelogram. Or you could say opposite sides of a parallelogram are congruent, but that's much longer. We could also say that BC has to be congruent with AD. Another definition of parallelogram. It's the exact same idea as what we were talking about there. Okay, and then we have 2 sides that are congruent. The last part, we don't actually need to use the parallelogram piece. If you notice, think back to our old days of proving triangles congruent. They share that middle side, AC. So AC can be congruent to itself. AC is congruent to AC. That's that reflexive property. So we still use the same ideas as what we were talking about before. And then lastly, now we have enough because we have 3 sides that are congruent for both triangles. So we can write the prove triangle DAC is congruent triangle BCA by side, side, side. Now this next proof is going to be using the fact that we have given information, but we want to prove it's a parallelogram. So it's going to be the opposite idea. We have to get to that idea that ABCD is a parallelogram. We're going to have to use the triangles, as you can probably guess. So the first one, just like usual, statement is angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. This is given to us. And then the next line that we would do is the way to go about proving this, ABCD is a parallelogram, is to either prove that lines are going to be parallel, opposite sides, or opposite sides are going to be congruent. We could also do the diagonals bisecting each other, but for this example, we only have one diagonal, so that's definitely not going to help us. We could show that consecutive angles are supplementary, but we don't know anything about A and C with their measurements, so that's also not going to help us. So the way that we're going to go about this one is actually proving that opposite sides are parallel. So if we look here, 3 and 4, if we think of this as our transversal, we know that 3 and 4 are congruent to each other. So that would force this line here and this line here if we draw these out, to be parallel to each other. Because if alternate interior angles are congruent, lines have to be parallel. This is the converse. So what we would say here is AB is parallel with DC. We would say converse, because it's the opposite idea, we're working backwards, of alternate, I'm going to abbreviate here so I don't run out of room, interior angles. The reason it's the converse is because we know the angles are congruent, so we're proving lines are parallel because of that fact. Then we can do the exact same logic just for the other angles. 1 and 2 have to be congruent because if we extend these lines, we're using the exact same idea of alternate interior angles, which is side AD has to be parallel with BC, and that is again the converse of alternate interior angles. Lastly, our goal was to prove ABCD is a parallelogram. ABCD is a parallelogram. Because we just figured out that both pairs of opposite sides are parallel, so we can just write opposite sides are, and you can do the parallel sign here if you want, parallel. All right, so that might have been really tough. I'm sorry if that was tough to follow. It's hard to do proofs, you know, when you're not in person. We're going to do some more practice in class though, so just do your best that you can, and I will see you, or you can ask questions